So let's see now, how do we train, what are we going to train our VAE on? So just a reminder, right? We've got our high dimensional space and our latent space, right? We've got these two. We talked about this in the previous video. And then we have our PX and our PSC. So if this is unfamiliar to you, I would check that out. Remember, the idea is that we're taking these guys, then we're learning a latent space, and then each of these will map to some distribution here. This guy will map to this distribution, and the hope is that these distributions will fill up the entire latent space, and then we'll be able to sample and generate new images, which is very, very great, or new data, whatever we're looking to generate. Okay, so let's, we're interested in this joint distribution. So the probability, right? This is a joint probability of observing X and Z at the same time. That's what probability of X comma Z means, right? The reason why is because if remember, back to the original goal, our goal is to maximize P of X. So we want to find a way of, we want to find an expression for P of X that we can then maximize. So P of X, right, can be written as the integral over all Z's. Let's see what this is saying, right? Again, this I'll have a video on marginal probabilities later on. But this is saying, this inside thing is the probability of X and Z occurring, right? Now, if we integrate over all Z's, we're marginalizing out the X probability. We're saying, okay, Z is kind of irrelevant here because we're accounting for all the possible Z's, right? We're accounting for all the possible Z values. So the probability of X and Z occurring just becomes the overall probability of X, right? You can think about it as if you have if you have a graph, what this would look like on a graph would be a 3D graph. So here would be like your X's, your X variable, and here would be your Z variable. And then the probability of, let's say, X being 2 and Z being 3 would be 2, 3 would be this point here, would be a certain height on the graph, right? And when you integrate this over the Z's, you're integrating along this axis, right? You're sort of like cutting your shape along this axis, and you're getting the probability of, you're getting a graph of, sorry, not along this axis, along your Z axis, right? So you're integrating along Z, right? And you're getting the probability of X, whatever that curve may look like. Okay, so this is why we're interested in the joint probability. So let's see what happens if we expand this out using a formula that we know, right? So the joint probability, the probability of seeing X and Z, means that first you have to see Z, then you have to see X, given that you've already seen Z, right? And that's a common formula. You should know that this will translate into these two. The reason why, again, as I explained, right, this is saying we want to see X and Z occur. So, okay, first we have to see Z occur. Then we don't just need to see X occur, we need to see the probability of X given Z, in the case that X and Z depend on each other, right? Okay, now the problem is, let's look at the terms that we were talking about here. So this P of Z, remember, is what this latent space looks like. This is what we want the latent space to look like. So in reality, all of these little blobs are gonna sum to something, right? And they're gonna add up to something. What we want to do is choose P of Z to be something that we want, to make it easy to sample out of. Because remember, the end goal is to pick points. And so we normally choose, there's a joke there, we normally choose P of Z to be normal with a mean of 0 and a standard deviation of 1. Or the identity, if you're looking for in multiple dimensions. I always think in 2 dimensions. So we want our P of Z to be a nice wrapper around all of these individual pools that has a mean of 0 and a standard deviation of 1. Okay, that's what we want the latent space, the overall latent space, to look like. Okay? So this is fine. what's p of x given z, right? This is what your decoder is learning, right? Remember, z is like your code and x is like your actual message. So p of x given z is what the decoder is learning. It's saying, okay, given a code z, can I reconstruct the actual x? Can I generate an x, right? For example, if your x's are images, then p of x given z would be some sort of maybe have, like, given a code for an image, you'll get back the specific image back. Okay. Now the issue with this integral is that this integral is what we call intractable, meaning it is technically possible to solve. There is a solution for it, but we are not able to find that solution. To keep it short, the reasons why are because, one, we're integrating over this dz, and even though z is a latent variable, it still could be quite high dimensional on its own, maybe 20, 50, 100 dimensions on its own. So integrating that is computationally not feasible. The other thing is that p of x given z is a very complex probability distribution that's modeled by a neural network, as we'll learn. And so it's hard to understand the shape of this. It's a very complex shape, and we've never been able to integrate it before. We don't really know how to integrate this thing. Okay, so here we're stuck, right? We're stuck because this is intractable. Okay, so we could give up, but let's try something else. So let me clear the whiteboard. Okay, I want to remind you of Bayes' theorem. Okay, and let's do a quick proof of it. The way I like to think about it is p of x given y. Okay, what's the probability of x given y? It's the probability of x and y occurring divided by the probability that y has already occurred, right? Now, the probability of x and y occurring is the same as the probability of y and x occurring, right? And the probability of y and x occurring is the probability of x occurring times the probability of y given that x has already occurred over the probability of y still, because this denominator stays the same. So pretty much what we've shown is that p of x given y equals to p of y given x times p of x over p of y. Okay, now you're like, why does this help us? Well, imagine we replaced this x's and y's with x's and z's. So now, all right, let's look at what we call the posterior distribution. So posterior, whatever you want to call it, right? This is saying, what's the probability of generating a code based on an input? And this is much harder, right? This is something that we're definitely going to have to model or approximate, because this is something that we need to learn, right? Let's see how it breaks down, right? P of z given x using Bayes' theorem will give us, we'll split into probability of x given z multiplied by the probability of z divided by the probability of x. And again, we have an issue. This computation is also intractable. Why? Because remember before, computing p of x was intractable because it dealt with that crazy integral. So computing, by the same way, computing p of z given x, because it includes p of x in it, is also going to be intractable. So we're stuck here, right? The idea, let's do a quick review, right? We choose our p of z, that's all good, right? That's what we choose to be normal, with mean 0 and standard deviation 1. We can model p of x given z, right? But p of z given x and p of x are both intractable. Okay, so here's where we're at. Let's come up with the solution. Let's introduce the solution, and then we'll go over the math. I keep saying we'll go over the math, but we'll go into the really nitty-gritty of the math in the next video. So the solution is we use this idea called variational inference. Terrible handwriting, I apologize. Okay, we're going to introduce this new guy here, which is going to be q of z given x. Okay, we will be able to, what this guy will output is it's obviously going to take in an x, take in an image. So it's going to take in image. Remember, my whole examples here have been images. So again, this could be any data, but it's nice to think about it with a concrete example. So take an image and output two things. It's going to output a mean, and technically it's going to output some sort of measure of variance. This could be your actual variance. This could be your standard deviation. This is always usually the log of your variance, but I'll get to that later. It basically outputs a distribution. That's what's important to realize. It outputs a mean and a spread, so you get a distribution. Okay, this is a key difference between variational autoencoders and regular autoencoders, is that a regular autoencoder will output just a point in the Z space. This will output a distribution in the Z space. Okay, the idea here, right, because we're not able to actually compute P of Z given X, we are going to try and approximate it as best as possible with Q. Okay, the way we're going to do this is we'll explain that in the next video. But that's kind of the main idea. So with that, hopefully you guys are excited to see the next video where all the math will come together and we'll derive the loss function, and it'll be very nice. So see you then.